Alright, now in the week 5 we're gonna complete the core part of the language. So with this week's while loops, so in principle any computation that is possible to express at all so can be expressed using just these language features. But then when we actually start solving problems, so we find out that some obstacles everybody encounters them along the way, and because they're so universal and so general, so then they have functions for them in the standard library so that we don't have to implement them. So let's generally not try to reinvent the wheel. We strive for the ideal that when some problem has been solved once, then it never has to be solved again by anybody, because you can just import the solution. But the while loop, so what's going on there? So now contrasting this to the for loop when you're iterating through a sequence. So now of course we could easily create a sequence that is so ridiculously long, so like lazily loop through the range up to 1 Google or something like that. So theoretically, so with the for loops we can already express any computation that could be physically realizable in our universe. But then with the while loop, so what we can express is repetitions where we don't know in the beginning how many steps we're going to take. So with the for loop, so you can make the range to be arbitrarily large, but whatever you make it is gonna be finite. Though then every for loop has a built-in upper limit how far it can run. But then the while loop, so as long as you can determine whether you have reached your goal that you're going for, so make a two-way decision on the spot. Are you currently standing on the goal that you wanna reach, yes or no? If yes, stay there and stop. The while loop terminates once you reach your goal. Otherwise, execute the body of the while loop, take one step towards the goal. So now your job is to write the body of the loop so that whatever the step is executed always takes you closer to the goal. Otherwise, you're doomed to wander infinitely long, never reaching the goal. And now, as our example, so this is probably somehow appropriate that our first algorithm example is the very oldest algorithm in the entire recorded history. So the Euclid from ancient Greece is known for the Euclid's theorems of geometry, and then for the proof that there exist infinitely many prime numbers. But then so is also the, at least in the record history, that whatever else is lost in the sands of time from Atlantis or whatever then. So then Euclid's algorithm is the oldest surviving non-trivial algorithm. So given two non-negative integers, then calculate the greatest common divisor, the familiar problem from when learning fractions back in school. So now this algorithm is also a good illustration of the principle that we can get to the goal using small steps or bigger steps. So we could already solve this problem in a very inefficient fashion by for looping through the range of potential common divisors, and then keeping track of what is the largest one that we have seen. But this would be horrendously inefficient, and then if a and b are like, let's say, 1000-digit numbers, so then we wouldn't finish in the lifetime of the universe. But going towards the goal is always better to put the magic boots on if you have them. So instead of taking one step, take like a 7-mile step like in a fairy tale. So the Euclid algorithm, so starting from the two integers a and b, and here now usually, so illustrating the principle that the silence is golden. The functions shouldn't be babbling, they just return the result, and then the caller can babble about it if they are so inclined, but it's their decision to make, not yours. But sometimes it's handy, so since we have these keyword arguments, so let's say that we have optionally can told to be verbose. So canonically, so this name verbose for the parameter that determines whether the operation should be babbling. So then here if verbose, so then we print the intermediate results, the current values of A and B. So let's say, so the Euclid's algorithm, so also illustrating, so the Euclid's realization, I think it was initially subtraction, but then whatever history of math that this was added, as long as B is greater than 0. So the goal is to make B to equal 0, and every while loop always while you are not on the goal. So not on this is always the negation of the thing that you want to happen. So we want to happen that B becomes 0. So this is the thing that we don't want to happen. So while we're not on the goal, so it is not the case that the B equals 0. So then we do something. Replace A with the value of B, and B is replaced by the remainder A. Remainder B. Notice that this expression always produces a number that is less than B, and therefore the value of B will always decrease. So then this will eventually reach the goal. So when you have a while loop, always get a reason somehow. So why is it that how do I know that I trust my faith that I'm on the right path, that I have the goal, that is it there over the horizon? I don't see it yet, so I just keep going. So how is it that this is guaranteed to reach the goal? So it is because the value of B, so it can be arbitrarily large, but it's gonna be decreasing in every step down the line. So if we now try this out, so let's say, so first without the verbose that I copied here, so this kind of made up number, and here is some small, this wasn't even a prime, but who cares? So looking for some common factors there, and then so if we give the parameter true, so let's have the intermediate results printed also. So A, so starting at the sorry, this is actually printing after. So after the first step, so A is that much, and then every step down the line. So notice how the remainder repeated application cuts a number down to size. So even if you had like 1,000-digit number, so chop. So this kind of when you get to do this kind of like a powerfully exponential thing, so even exponentially big things come quickly down to size. That's another principle that we'll encounter later. But to this, the important thing, the while loop. So while, and this is always the negation, the thing that you don't want. So this is the negation of the thing that you want. So then you gotta keep going when you're standing on the goal. And notice a common edge situation. If you're already standing on the goal to begin with, so it's perfectly possible that this test is false to begin with. So then the while loop correctly does nothing at all when there is nothing to do. So then in that situation, if we did anything, change anything, so then whatever we did, the change was incorrect. So the while loop correctly does nothing at all when there is nothing to do.